there is a problem in forming the group, uh, by yourself, then I may not have a choice but to then assign you the groups, right, by myself. So my request to you is that by the end of the week, please try to work this thing out among yourself. If you tell me for the help, I will not have a choice but to then just form the group based on the student IDs. And I'll have to do that because I don't know any other way. I cannot pick the students who are your friends and all that, right? So I got several emails, and I am requesting you all that please help your friends, your classmates, because I'm also getting an email saying that there are some students who doesn't know anyone, or they don't have enough friends to form a single group. So they are saying that we don't have enough people in the group, or some people are saying that we five of us are there in the group, but we don't know coding or anything like that. So I'm getting all kinds of emails from your batch. So I request all of you to work among yourself, help each other out, and make sure that these groups are formed by the weekend. If not, then by Monday I'll be forced to do the groups using the student IDs. Okay, so I can give you the freedom, but then you have to work among yourself. Okay, that is what I would say. All right. uh, any questions that anyone has before we begin? Okay. Is my screen visible?
Yes, sir.
All right. So I'm not sure who had requested, to do the groups among yourself only. But those who have requested and those who are in the agreement, please try to work with the other students who are not able to form the groups on their own, right? Because I don't want this issue to continue for a longer time. And rather than actually working on the technical stuff, we spend time in figuring out which group will be having which students. So try to resolve this as quickly as possible. If you need my intervention in forming the group, then like I said, the only thing I can do is that I can go by student ID, and I will just say that these students IDs are the groups, right? Okay. So now we were looking at the kill system call in the previous lecture, and what we were saying is that you can send the signal uh, using the kill system call. So kill is actually originally the kill system call was used for sending the kill signal only, but actually the kill system call is used for sending any signals to any of the process, right? So there's a process ID that you can provide here, and then there is a signal code that you can also provide, and using that you can send a specific signal to the process ID. Okay. uh, so basically there are four options, or actually five options, that you can provide in terms of the process ID. If you provide the positive integer value for the process ID, then this particular signal will only be sent to that specific process ID. So if I say kill 10 comma SIGINT, right, then the SIGINT will be only sent to the process ID 10. If you provide a negative value, so if I provide kill minus 10 SIGINT, right, if I provide that, then basically what it will do, it will use 10 as the PID, and it will basically find the process group ID for the process ID 10, right? So process ID 10 will obviously have some group ID. So it will grab the group ID of that process ID, which is 10, and then it will send that signal to all the processes that belong to that same group ID. Okay, so let's assume that there is a parent process which has a PID of 10, and then there are two child processes, PID 11 and 12, right? And all of these three processes belonging to the same process group ID, which is 10, right? So if you say minus 10 here, it will find the, so that 10 you are providing is the value of the process ID. And since the negative value is there, then the operating system will say that, okay, find the group ID of that process ID 10, which is also 10. Now you send the signal to all the processes that belong to the same process group ID. So again, that second signal will be sent to the parent process as well as the child processes. Okay. If you provide 0 value, then it will again do the same thing as sort of like a negative value, that every process in the same process group. So here you are not actually providing a specific process ID, but you are saying the current process. So whichever process is calling that kill system call, for that process it will find the process group ID and it will send the signal to all the processes. In this case, you can actually send it to another process ID also, right? So in this case, you can provide a different process ID also, whereas in this case you are saying that the current process. And then you have these two other options which we don't need to use, or we don't really use, because this is kind of going to be killing your system, right? So the first three are the important ones that you should understand, that what are the options and how do we send the signal. Okay, so what we will do is that we will actually use this kill system call to send a signal to another process, and we will also take a help from one more signal, or we'll also use another signal in the parent process, which is also called sick child signal. So I'm not sure if we had looked at any of the example for the sick child signal. No, I don't believe we have. So sick child is the signal which basically says that this signal is sent to the parent process when the child process terminates. Okay, so whenever the child process terminates, that time the parent process will be getting a sick child signal. Okay, so normally, if you recall, when we looked at the process management code, right? Let me show you that. So if we look at the process management code, we had looked at an example of master slave implementation. And if you recall, in this master slave implementation, what we had done is that we had created n number of child processes, and then for each of the child processes we implemented the wait, right? So this wait wait system call is also needs to be executed in the main function here, because we do not know in the parent process at this time that when is the child process going to terminate. Okay, so once all the once all the processing of the whatever parent needs to do, right, all of that is done, then you basically go into this wait mode, and in the wait mode the child process will be terminating one by one, and then you are issuing that many waits, so for every single child you come out of the wait mode, right? So this is what we had seen when we did the process management, because we did not know that there is a signal that will be sent, or that can be sent by the operating system to the parent process when a child process terminates. Okay, so now what we are going to do is that instead of using this wait system call in the main function, right, and having the parent process hooked on to this or blocked for this wait system call, we can actually issue the wait system call when the sick child signal is received by the parent process. Okay, so what we can do is that we can actually, this is one blocking call, right, and then the parent process can continue to do other type of processing, right? So for example, what we will basically do is, again, we will modify the parent process. The child process will remain the same. So when we go and look at that child process, you'll recognize what the child process was doing earlier. So this was the child process we had, right? So it was accepting two arguments. We convert the values into the numbers. We calculate the sum, and then we provide the sum in the exit code, right? So this was the same code that we used in the process management for the child process. However, for the parent process, we modify a little, right? So what we do, so now we know that there is a signal called sick child. Sorry. And the sick child signal will be received by the parent process when any of the child process terminates. Okay, so we are going to implement this handler, right? So sick child handler will be implemented, and whenever any of the child process will be terminated, this handler will be executed. So you can see that in the handler, what we are doing, we are actually putting the wait call inside the handler. So wait call is a blocking call. So instead of having parent blocked for this wait system call, we actually put that inside the handler. And so what will happen is that now you can actually do other things, other activity in the main process also, while when the parent process is executing. So you can see what we have done is, instead of getting the values from the command line argument, right, we are actually using the scanf. Now scanf is also a blocking call. Why it is a blocking call? Because it is accepting the data from a user. So until the user enters some data, this scanf system call will not come out, right? It will not be finished. So that means that there is a blocking call for scanf, and also there is a blocking call of wait. So you could not actually implement this particular code without a sick child signal. Because if you were to do scanf here, and then if you were to do wait call at the end over here, both will be contradicting each other, right? Conflicting each other, because either the main process or the parent process will have to wait in the scanf, or the parent process will have to wait in the wait, right? So both cannot be done at the same time. Both cannot be done simultaneously. So what we do in the main function, right, where the parent process is running, we are putting a scanf here, right? But then we implement the sick child handler, and in the sick child handler we put the wait. So what will happen is that the parent process will never be actually blocked for this wait system call, because we know that when the sick child handler is called, the child process has terminated, right? It has terminated. So immediately when the parent process executes this wait call, it will just receive the child process ID, and it can receive the additional information in form of status, and then that's about it, right? So you can then get whatever information you want from the status, and you can immediately come out. So in short, what I'm saying is that every time when a child process terminates, this handler will be called, okay? Because each time the child process terminates, the sick child signal will be sent to the parent process. So instead of having to wait in the main function itself, the parent process can implement this sick child handler, and so that you can actually remove that infinite waiting on the wait system call. Okay, so this is how we can actually implement the sick child handler. And by the way, I think this one doesn't have the example of sending the signal using the kill command, but I think it will be in the next example, which we will look at. So this example is actually just primarily talking about how to use the sick child signal. So let me just execute this code. So parent or process parent. So now what will happen is, if I enter these two values, right? Let me say this, and then now the screen comes back. The child process has started, and now I can enter another set of values. I can set another set of values, and you can see that these child processes are running right in the background. now you see that this message is actually coming from the SIG child handler, right? So the child process finished here while the parent process continued to read the data from the user. Okay, so what I'm trying to say is that you actually separated out two blocking calls, the scanf and the wait, because we had two different because we implemented wait system call inside the SIG child handler and not in the main function. Okay, so this is basically what you can do to remove the blocking calls for two blocking calls within the parent process. Okay, now let's look at how we can use the kill system call, right? So in order to use this kill system call, we know that the SIG child is the signal that is received by the parent process when the child process finishes, right? So what we are doing in this code is, so you can see that in this particular code we are using multiple concepts. We are using the concepts of running different program or different application in the child process. We are also using the concept of the signals. We are also using concept of sending a signal using a kill command and so on. Okay, so what we are doing in this program or in this application is that obviously we have the handler, the SIG child handler, which is the same kind of thing what we did earlier. Only additional thing is that we put exit here. So what does this mean? That the first time itself when the parent process will execute the handler, the SIG child handler, the parent process will terminate also. So after the handler is executed, the code for the handler is executed, we don't want the parent process to continue. Okay, so we are saying that as soon as the first child is terminated, we want the parent process to also terminate. So that's why there is an exit command here. So that is one thing that I want you to look at, right? Second thing is, what we are doing is, after setting up the SIG child handler, we are checking whether it is a child process or a parent process. If it is a child process, we are actually running a separate application, separate program here as a argv2, which is going to be provided as argv2, right? And in the first argument, we are actually providing the delay. So we are not specifying the delay as a hard-coded value 5 or 10 or 1 or 2 or whatever. We are actually reading the delay value from the keyboard, from the command line argument, right? So we take the command line argument, and whatever is that delay that we have is stored here. So scanf is basically string scanf. So this is a string value, and from that string value, it is going to be converting that value into integer, and that value will be stored in this variable. So that is what the scanf. This is how the scanf works. Okay, so we read the delay value, and that is the delay that we provide into sleep command. Okay, and then we are killing the SIGINT. So basically what we are saying is that if my child process, whatever the command that I provide in the child process, if it took less time, right, then this particular delay, then the child will be terminated, right? And then as soon as the child gets terminated, the parent process will get a SIG child signal, and then the parent process will be terminated here. Okay, what it means is that if the delay that you provide is longer than the amount of time it takes for the child process to terminate, to child application to finish, then you get this message that child is terminated within X number of seconds. Okay, which is the seconds that you provided. Okay, and then the parent process terminates. But if you run the application here, which takes longer time, then this delay is provided, right? So let's say the delay is 2 seconds and this application is taking 5 seconds. Okay, in that case, what will happen? This delay will be over first, right? And so you actually get this printf statement, right? So you say that child is exceeded the limit and child is being killed. And so what will happen is the parent process now will send a SIGINT signal to the child process. and then the parent process will be terminated, will be finished, right? So basically what will happen is that if the child process takes less time than the amount of delay provided, then the sick child handler gets executed and this message gets printed. Okay, but if the child process takes longer time, then this message gets printed, right? And the child is getting killed by a SIGINT signal. So these are the two actions that are these are the two paths that this application is taking. Okay, so let us execute and show you how that works. And so this is the example where we are using a kill system call to send the SIGINT signal to the child process. Okay, so the code is called child death detection. Okay, so now the first command line argument that I need to provide, right, is the delay. So let us say that I will provide a delay of 5 seconds. Okay, and the second argument that I need to provide here is the program that is going to be executed, the application that is going to be executed, right? So I'll provide here ls. Okay, so when I provide ls as an application that is executed, obviously ls is not going to take 5 seconds, right? So what will happen? The ls command will get executed as part of your exec command, your exec system call, and so the child process is basically now executing the ls, and the parent process is saying that the child process is terminated within 5 seconds. So what happened was that in this example, in this case, the child process finished earlier. So when the child process finished earlier, the sick child signal was sent to the parent process. So this the child handler was executed and this message was printed by the parent process, and then the parent process also exited. So this is the path that was taken when we execute this particular command. Now let's say if I provide a different command that takes more than 5 seconds. Okay, so what I will actually do, I'll actually provide a sleep command and I will sleep for 10 seconds. Right, so I'm basically saying that now the child process will be sleeping for 10 seconds and the parent process is actually sleeping for 5 seconds. Okay, so therefore the child process obviously will take longer time to run compared to the parent process. Okay, and so the expectation is that the child process has to be killed by the parent process, right? So now you can see that when I run this, it is saying that the child process exceeded the limit and it is being killed. So in this particular case, the child process took longer time, so therefore the sick child signal was not sent to the parent process, but the sleep delay was was finished or timed out before the child process got finished, and so we actually print this line, and then the SIGINT signal was sent to the child process to kill it. Okay, so this is an example of showing you how you can use exec command, how you can use kill command, how you can use signal, sick child handler, and so on, right? So multiple things can be combined. Even in this 15-20 line of code, you can see that we can actually combine multiple concepts, right? So this is the kind of thing I would like you to think about when you are working on the projects. But obviously you also want to include something like file IO and pipes and other things, right? Okay, now we look at two more signals, right? Am I still audible?
Yes, sir. Yes, sir.
Okay. I just want to make sure I'm not disconnected. All right. So two more signals, sick stop and sick continue. So if you recall, what we said about sick stop signal is sick stop is used for putting the process in the suspension mode, okay, or a sleep mode, whatever you want to call, right? So that means that the active process, while the process is running, right, if you send a 6-stop signal, it will be basically put in the suspended mode, which means that the process uh, may not be running, and it will be just sleeping, right? It will not be occupying any processing resources. Okay. Now let us say that you had a process in the sleep mode or suspension mode, and you want that process to come back and run again, right? So in that case, you would be executing the SIG continue signal. Okay. So usually, the context switching, when the operating system does, it uses the SIG TSTP and SIG continue signals. This signal can be used by also. So there are, if you recall, there are two signals for stopping. One is TSTP and one is stop, right? So you can see this one, right? So TSTP signal is used when you press Control Z. That will also put the process in a suspension mode. Okay. And then this particular signal that we are looking at now, 6-stop, is a signal which is unblockable. So this signal you cannot override, and it is generally used by the operating system during the context switching time, right? So when the process gets a 6-stop signal, the process will be going into sleep mode or suspension mode, and the processing resources will be taken away from the process, right? It will be assigned to somebody else. And then when the process needs to again continue running, then the SIG continue signal will be sent by the operating system to the processor, so that the process now again gets the CPU allocated, and then it will start running again. Okay. It is also used, you can also use Control Z key combination and FG command combination to do the similar kind of thing. Okay. Or context switch time, operating system will do it also. So the example that we will see is where I want the process to be going into the suspension mode, and then I will bring back the process again, in the active mode. So how do I show you that example? So what we have done is we have actually created two child processes. So we have the fork done here, and if it is a child process, then it will go into this particular loop, right? So the condition is obviously false for the parent process. So parent process will go down here, but the child process will be continuing in this particular loop. And what this loop is doing, in this loop, we are just displaying this message and sleeping for 1 second. So which means that every 1 second, this message will be displayed by this child process, which is the first child process. Okay. Now the parent process will continue. It will create another child process. And again, the same second child process will display this message after every 1 second of sleep. Right. So which means that you have two child processes. The first child process displays PID1 is alive after every 1 second. Similarly, child number 2 displays PID2 is alive after every 1 second. Okay. So again, these child processes are hooked onto this while loop, and the parent process again falls down here. So this part of the code will be only executed by the parent process because the child processes are already in this while loop. So what the parent process now will do, it will sleep for 3 seconds. So during these 3 seconds, we can see that both the child will be running, right? And because we have a sleep for 3 seconds, we are expecting that PID1 alive message will be printed 3 times approximately, because it will be printed once after every 1 second. And similarly for the child 2 also, this message will be printed after every 1 second. So we are expecting that PID1 is alive message and PID2 is alive messages will be displayed about 3 times, okay, in these 3 seconds of sleep time of the parent process. Now what the parent process is doing, it is putting the child 1 into suspension mode by sending the 6-stop signal. Okay, so child 1 will be going into suspension mode, which means that during this second phase of 3 seconds, right, seconds 4, 5, and 6, during these seconds, the child 2 is active, but child 1 is sleeping, is suspended, which means we are expecting that during those seconds, this message is not displayed. This message is not displayed because child 2 is suspended. Then after those 3 seconds are timed out, seconds 4, 5, and 6, then during the 7th second, the child 1 is again activated by sending the SIG continue signal. Okay, so when you send a SIG continue signal to child 1, the child 1 gets activated again, and again during these 3 seconds, which is the second 7, 8, and 9, we are expecting again both child to start printing the messages after every second. So again, we are expecting 3 messages from child 1 and 3 messages from child 2. And then finally, after the 9th second, we are killing both the child. Okay, so this is the code. This is what is showing you that you can put a process into suspension mode and you can bring again the process into the active mode. So let me show you that execution. Okay, so now when we take a look at this output, right, what we are observing, these here, these are the messages that we got during the first 3 seconds. Okay, now we can see that PID1 is alive is actually done 4 times. Similarly, PID2 is also done, no, PID2 is done 3 times. Okay, why that is? Because like I said, each child process and each parent processes are running on a separate core. So what happens is that by the 3 seconds of the parent process was timed out, by that time actually the child process, so this line, right, this line was printed almost immediately after the first second started. Okay, and this line was printed almost immediately before that 3 second was elapsed. So for example, if you print this message at 0.01 second and this message as 2.59 seconds, right, then you could get something like this. Okay, so again, as I said, we are expecting to have 3 messages from PID1 and PID2, but it may be possible that you may get 1 extra message or 1 less message, depending on what was the clock at for that specific processor when the child process was allocated to that processor. Okay, so this is the first 3 seconds, okay, during which both the processes are printing the messages. Then these are, again, you can see that these 3 messages are during the second phase of those 3 seconds. So seconds 5, 4, 5, and 6. During that time, we don't get messages from PID1 because it is in the suspension mode. And then you look at this last 6 messages again, right? These are the messages again when the PID1 is sent a continue signal and it is able to run again, right? So again, if I keep on running this application multiple times, you will find that we will get different set of outputs every time. Okay, we will get different set of outputs. So here you will see that I got the PID thing printed only 3 times, 1, 2, and 3. And now the second 3 seconds or 4, 5, 6 seconds, you get only PID2, and then here you get again PID1 and 2. So what I'm trying to say is that every time you get the different output because both the child processes and the parent processes are allocated different cores. Okay, and the execution of each of those processes are not in our control, but it is controlled by the operating system. Okay, any questions? Is it clear? I mean, are you able to follow along with me? Yes, no, maybe. Does the stack of the process remain the same when the... So when you say Krupal, what do you mean by stack of process? Yes, what do you mean by stack of process?
Like
Sorry, you are breaking up very bad. I can't hear you. I mean, I can't hear anything. It's a lot of noise that you are getting in your microphone. Okay, let's do one thing. I'll process ID and program counter. Process ID is for process IDs for the child processes and the parent processes are different, right? So which means that you have three different process IDs, and each of these processes are allocated a different processor, which means they have their own program counter. Okay, so child process can run on, let's say, core 1. Child process 2 can run on core 2. Parent process may run on core 3. Right? Each of these cores have different program counter. Does it make sense? Okay. All right. Any other question anyone has? Okay. So we look at two more signals, SIG user 1 and SIG user 2. Right. Now these are the signals which operating system has provided to us as a user defined signal. What does it mean? It means that there is no default action or default event associated with these signals. So there is no event that happens in the operating system or at any system level event that will cause these signals to be generated or this signal to be sent to a process. So these two signals are kept by the operating system to be used only by programmers like us, who is going to be using it as a user defined signals. Okay. So the question is, where would you use these kind of signals? Okay. So I'll give you one example. I don't believe I have given you that example as with the implementation, but I believe this example is there in the lab assignment, I believe, and that is something that you will be required to implement. So the example is when we were studying pipe. Okay, what I mentioned is that the pipes are unidirectional pipes. What does it mean? It means that at a time, only one of the process, either parent or child, can write into the pipe, and the other process can read from the pipe. So let's say the data is being sent from the parent process to the child process. Okay, then parent process can write and the child process can read. But at the same time, child process cannot write and parent process cannot read, because otherwise the data will get jumbled and we will not know who actually has sent what data. So but you want to use that same pipe for bidirectional communication, even though bidirectional, when I say bidirectional, it does not mean sending the data exactly at the same time. Normally bidirectional means sending the data exactly at the same time. What I mean to say is that you want to send the data from both the processes to the other process, but one after the other. Okay, but when you want to do that, there has to be something called as handshaking, right? Or some communication method which basically tells the other process that I'm using the pipe, so you don't use the pipe, right? Meaning for writing the data. So let's say if parent wants to write the data, then it will have to inform to the child process that I am using the pipe for writing the data, so you don't write anything. So what you can do is you can use, let's say, sig user 1 for that. So whichever process wants to write the data into the pipe, whether it is a parent or the child process, they will have to, one of the, that process who is going to be a writer process will have to send the data, will have to send the sig user 1 to the other process. So let's say parent is writing into the pipe, then parent will send sig user 1 to the child process. Once the child process receives the sig user 1, it will not use the pipe for writing. Okay. Once parent process is done writing the data into the pipe, it will send a sig user 2 to the child process, and the child process will be able to read that data from the pipe. Now the pipe is empty. Okay. And now the pipe is again available to any of the processes. So if now the child wants to write the data into the pipe, the child will send sig user 1 to the parent process. And once it is done writing the data into the pipe, it will send sig user 2. So what I'm saying is you can use sig user 1 and sig user 2 to intimate, right, to inform the other process that I am going to be writing into the pipe or I'm done writing into the pipe. This is something that you can use the sig users. And this is why I'm saying that operating system has not decided which event can be used for sig user 1 and 2. It is up to us as a system programmer to use any event associated in our application with which we can then use the sig user 1 and 2. Okay. So here I'm going to show you another type of application for for a sig user. So let us say that you want to have synchronized activity among all the child processes. So let's say you have a parent process, okay, and every 5 seconds you want something to be done by all the child processes. Okay, how would you communicate that? How would you handle that? So what you can do is you can actually set this alarm, set the alarm for 5 seconds in the parent process, and once the alarm is timed out, the parent process will get the sig alarm signal, right? So once the parent process gets a sig alarm signal, it can actually then send a sig user 1 to all the child processes. And when the child processes receives the signal, they will do an activity which was predetermined to be done at every 5 seconds. So what I'm saying is you can even do the synchronization of a common activity between all the child processes by using this, again, master slave combination, right? So parent is your master, which is informing what needs to be done to the child process, and then the child process will act accordingly. So this example I have, right? The other example, it's not there, meaning it's not implemented, but that is something that you will be required to implement as part of your lab assignment, I believe. So here what we are doing is, as I said, we have a sig user 1 and we are implementing the handler for sig user 1, right? So what is the handler for sig user 1? The handler for sig user 1 is currently just displaying the message. Okay, but you can basically do whatever activity that you want, which is the synchronized activity that can be implemented in this signal handler. Okay, now the parent process is going to create a child processes. Okay, so what we are doing is, if it is the parent process, we continue. If it is the child process, we come out of the loop, right? So every time the loop works, every time the loop goes, the child process will break out, but the parent process will continue. Okay, and each of the child processes PID will be saved in this array. Okay, so we have an array declaration of 5, which is here, child PID of 5. So for each of the child PID that we receive, it will be saved into this array. Now, once the parent process is done running this for loop, right, it will obviously come out. Now, even the child process will come out from the loop in each iteration. So what happens is that in the child process, for example, it is going to check for this condition, but this condition will be false because the parent PID is saved here, and this PID is only going to be the parent process PID, right? So this condition will be false for every single child process. that we create. So the child process will just go here and it will be waiting into the infinite loop. Okay, so all the five child processes will be only doing this infinite loop. Okay, but once the parent process is done with this for loop, and once it comes out here, then this condition will be true for the parent process, right? So in the parent process only, this alarm is set. So alarm will be set in the parent process, and the signal handler is set for the SIG alarm. So once these 3 seconds are timed out, then the signal handler for the SIG alarm will be called, and this is what we are doing there, right? So what we are doing, we know that there are 5 child processes which we have created. We use the kill system call to send SIG user 1 to each of the child processes PID. Okay, so in the SIG alarm handler, so this handler is going to be executed only by the parent process. Okay, and then the parent process will be sending a SIG user 1 signal to each of the child processes. And so each of the child processes will get SIG user 1, and they will be executing this particular handler. And that's about it, right? So SIG alarm handler is executed only by the parent process. However, SIG user 1 handler is executed only by the child process. That is something you can control again like this. Clear to everyone? Any questions? Any doubt? So let me execute this line of code. SIG user sync example. So these are the process IDs. The parent process ID is 32571, right? And the child process IDs are 72276, right? So you can see that once the 3 second timed out happened, only the child processes received the SIG user 1 signal, right? So we send the signal from the parent process to each of the child processes, and each of the child processes are handling the signal for the SIG user 1. Now, I didn't print any message from the alarm signal, but you could do that, and you would have noticed that that alarm SIG handler is only executed by the parent process. Okay, so you could actually print something over here in case if you want to know that this signal handler is executed only by the parent process. Any questions? Okay. Now in this example, again, we are using SIG user 1 and 2. Now in this example, I'm not implementing pipe, so to speak, but I'm giving you kind of the way we would be implementing the communication between the two processes by using SIG user 1 and SIG user 2, right? So in this example, we only use SIG user 1 in along with the SIG alarm, but in this example, we will use SIG user 1 and SIG user 2. So in this process, basically what we are doing is we are first having the child process send SIG user 1 to parent. Okay. Once parent receives the SIG user 1, it will send SIG user 1 to the child process. The child, when it receives SIG user 1, it will send SIG user 2 to the parent process. Then the parent process will send SIG user 2 to the child process. Okay. And then when the child process receives the SIG user 2, it will terminate itself. Okay. It will basically terminate itself by sending a SIG signal to itself. Okay, so as soon as the child process terminates, the parent process will also die because we have a wait system call, and after the wait system call, we have exit, right, for the parent process. So in this example, I'm just trying to show you that you can actually use both SIG user 1 and SIG user 2 to communicate between the two processes. One additional thing that or two additional thing that I'm going to show you is where we can actually implement a single signal handler for multiple signals. So you can see that in the main function here, right? What we have done is we have a sig user 1 and whose signal handler is also this, and we have a sig user 2 and we have the same signal handler for the sig user 2 also. So we have two signals which are handled by the same function, same signal handler function. So how do we do that, and how can we achieve that? That is something that I will also show you in this example. Second thing that I want to show you here is that you can see that this piece of the code is done before fork. Before fork. What does it mean? It means that this code also shows that whatever signal handling that the parent process has will be inherited by the child process when the fork command is executed. Okay, so since we have set this signal handler for the parent process, for the main process, once we do the fork, the same signal handling will be inherited by the child process also. Okay, so these two concepts are being shown in this particular example. Okay, so once we set this handler, we do the fork, and after the fork, the child process, as you can see, is sending the sig user 1 to the parent process. Now, why do I say parent process? Because you will see that before the fork, we have captured PID 1. Okay, and when we capture PID 1 before the fork, this means that this process ID has to be the parent process ID, because we know that the main process basically becomes the parent process, right? And the PID 2 is captured from the fork when the when you capture this, in this case, your PID 2 will be storing the child process ID, right? In this case, we will be storing the child process ID. So PID 1 will have the parent process ID, PID 2 will have the child process ID. That is what we are confirming here. So first, the child process will be sending the sig user 1 to the parent process, and then it will go into the infinite loop, right? It will go into the infinite loop. Now, if it is not the child process, then it will go into the else mode, and else part we will have the wait. So which means your parent process will actually be in the wait call here, right? So parent process will be continuously waiting in the wait system call. Now, since we have sent a sig user 1 signal to the parent process, while that parent process is in the wait call, the signal will be actually sent to the parent process from the child process or by the operating system, right? So the parent process will now execute the signal handler, which is this particular signal handler code, right? So what is this code doing? So if you look at this code, basically what it is doing, it is accepting one parameter here, and this parameter we have not seen earlier, but what this parameter is doing, every single signal handler that you implement has a single integer value that is used as an argument. Okay, what this parameter says is the signal number that caused this signal handler to get executed. Okay, so since we have used the same signal handler for both the signals sig user 1 and 2, this value is important for us, because we need to understand whether the signal handler was called because of sig user 1 or because of sig user 2. And that is what we do first, right? So first we have this switch statement, and we are checking whether the signal that caused this handler to get executed was the sig user 1 or sig user 2. So in this particular case, right now, we know that the child process has sent sig user 1 to the parent process. So when we come to the handler, when the parent process is executing the signal handler, this number will be sig user 1. So this case will be true. This case will be true. But now, when we know only that the sig user 1 has caused the signal handler to execute it. But how do we know that which process is actually executing this signal handler, whether it is a parent process or the child process? So what can we do? We check this condition. We check this condition. So we say that the current process, get PID is the current process, who is executing this code, is that PID matching with the PID 1 or PID 2, right? So if the PID 1 is the PID for this current process, that means that it is the parent process who got the sig user 1, right? So in this case, we will have this condition as true, because yes, the signal handler is executed by the parent process for sig user 1. So this condition will be true, and therefore what we will do, we will be sending sig user 1 to the child process, right? So PID 2 is the child process in the parent process. So in the parent process, when you look at it, PID 2 will have the value of child process. So we send sig user 1 to the child process. Now this handler will be called by the child process. Okay. So now again it is a sig user 1, so this switch case will be true. Okay. But now when we do the comparison here, this condition will be false, because the PID which is currently now running this handler is actually the child process. So therefore we will go into the else part. Okay. When we go into the else part, what we are doing, we are sending sig user 2 signal to the parent process. Okay. So now parent process will get sig user 2 and it will start executing this signal handler. So this value will now be sig user 2, and this switch will not be true for the case 1, but it will be true for the case 2, right? So now it will come over here. This condition will be true. This case will be true. And now we again check whether it is a sig user 2 for a parent process or a child process. Now we know that it was sent to the parent process, right, by here. So that means this particular condition will be true. And therefore, now we are sending sig user 2 to the child process, right? So when we send sig user 2 to the child process will execute this handler. Okay. And when the child process executes this handler, again the case of sig user 2 will be true, but then this condition will be false, right? This condition will be false. And so this is the command that will get executed. And what is this command? It is basically sending a SIGINT signal to the same process ID. Get PID is the same process ID, which is the child process. Okay. So child process basically will kill itself. Once the child process kills itself, the child process terminates, and therefore the parent process which was here in the wait system call will come out, and then it will execute all these remaining thing to check how the child process was terminated, etc., and then it will come out of the main function. So this is how this particular code is working. So in this example, I'm showing you that single signal handler can be used for multiple signals. Even you can check within that signal handler that which process has sent what signal. That can be checked also. And the third thing that we are learning here is that the signal handler that is set before the fork, right, in the main process is inherited by the child process. Okay, so the parent process and the child process uses the same signal handler as long as it is set before the fork system call. So these three concepts are basically being used in this code, and I believe these are the important things to know about signals. Okay, any questions? How this code is working? Hope I'm not disconnected. Are you guys able to still hear me?
Yes.
Okay. All right. So let me run this code. It's called sig user test. So the output is something like this. you have the parent PID and the child PID, and each time when a process is sending a signal to another one, we are getting these messages, right? So first child is sending the sig user 1 to the parent. Now the parent process received the sig user 1. The parent process is now passing sig user 1 to the child process. Now the child process receives the sig user 1. Now the child process is passing sig user 2 to the parent process. Parent process receives the sig user 2. Now the parent process is passing sig user 2 to the child process, and the child process receives the sig user 2, and then finally the child process is terminating itself. And so this message is again coming from the parent process after the wait system call, right? So it is basically determining, or it is able to understand that the child process was killed because the SIGINT signal was sent. Okay, so this is how this particular piece of code is running. Okay, now we have looked at, I think, most of the important signals that are available in the system, and I mean, I think this up to this information, whatever we have covered so far, I think has given you quite a bit of understanding of how the signal works and what are the different signals and how can we use them in different scenarios, right? But what happens is that, let's say you are already, the process already has gotten one signal and it is already executing that signal. Now it is also possible that while that process is executing the signal handler, maybe another signal was sent to the same process. Okay, but you want that in this particular signal handler only this signal is processed, no other signal has to be processed. So you want to kind of disable or block other signals in a signal handler. Okay, so for one type of signal, when you receive one signal, within the handler of that signal you want to disable the other type of signals, maybe not all but some of them, right? So how would you handle that? So that is why this example is that ignore other signal inside the signal handler. So how would we do that? So what we can do is we basically modified a code a little bit yesterday. So basically what happens is that, let's say in this process we have two signals we are considering, SIGINT and SIGQUIT. Okay, so what we are assuming is that we get a SIGQUIT signal. Okay, so when we are handling the SIGQUIT signal, within the SIGQUIT signal, I want to disable the SIGINT signal, for example. Okay, so I don't want the SIGINT signal to be to be handled while I'm executing my quit handler. Okay, so what I will do, again, in this process I'll be sending this SIGQUIT signal. I'm using this 5-second sleep so that these handlers are set properly, right? So I'm giving a little bit of delay because of that. Okay, and then I will send this SIGQUIT signal to the process. So once I send the SIGQUIT signal to the process, obviously the quit handler will be executed because that is what we have set over here. So within the quit handler, we are setting that you ignore the SIGINT signal, right? So we are setting that you ignore the SIGINT signal. So during this quit handler, SIGINT signal will not be entertained, right? And then we have sleep for 5 seconds just to make sure that we have sufficient time for handling the quit handler. And then finally, once the handler is done, then we are going back to the int handler, which is which was the original handler we had set over here. So we set the original handler for SIGINT as int handler, and in the int handler all we are doing is just these two printfs. That's all, right? So what we are saying is that during the quit handler, the SIGINT signal will not be entertained, but otherwise the SIGINT signal will be entertained. So during these first 3 seconds, the SIGINT signal will be entertained, right? But then after that, once the SIGQUIT handler is getting executed in the second phase of this 5 seconds, then the SIGINT signal is not entertained. Okay, so that is the example that we are showing you. So if I do this, and if I press Control C now, obviously you can see that the SIG signal is handled, because I do get this message: received SIG signal 2, waiting, leaving. Right. So this is basically the handler, right? Int handler that got executed over here. Right. That is why we got this message. Right. But then if I would have waited for the first 5 seconds, uh, so let me wait now for the 5 seconds. And now if I do Control C, nothing happens, right? So when I'm in this quit handler, then the Control C is disabled, so nothing happens. Okay, so this, obviously we have seen how to disable and enable the signal, right? So the same thing you can do within the signal handler also. But there is a problem with this. Okay, what is the problem with this? The problem with this is that, let's say you want to disable many signals. Okay, you want to disable many signals. What does it mean? It means that for each of those signals, you have to actually write something like this with the different signal numbers. So each of the signal you want to disable, you will have to write the signal number here, and you have to do sig IGN, sig IGN, sig IGN. Now let's assume that you are at line number 2. Okay, and the signal which is disabled at, let's say, line number 5 actually was received by the process. Then obviously that signal will have to be handled, because that signal is not yet blocked, right? It is not yet blocked. So we need a mechanism that will allow us to block and unblock set of signals at the same time. Okay, not one signal at a time, but set of signals at the same time, right? That is where this new additional functionality that I'm going to talk about briefly is there. So there is a new system called SIG action. So in this SIG action, this is more like a signal only, but it is an advanced version of signal. So in this case, what we do is that we provide actually the structure, right? Instead of providing the function pointer, we are providing the structure. And in this structure, we have this action, right? Or, where you can provide the action that you want to take, right? Either customized handler, or ignoring the signal, or the default action, right? So you can provide the handler. In addition, you can provide this information, right? This third member of the structure is called mask, right? SA mask. And this SA mask is nothing but a number of signals, right? The set of signals that you can provide to block that many signals while this handler is getting executed. So while this handler is getting executed, all the signals, the set of signals that you provide here, all of them will be masked together. Okay, and how do we create this mask? How do we create this set of signals? So for that, operating system has provided these macros, right? So these macros are provided. So you can either create an empty set of signals, you can create a full set of signals. So when you use sig fill set, it means all the signals will be blocked, right? So this set will be created with all the signals in them. You can add a particular signal to the set, you can delete a signal from the set, or you can check whether a particular signal is part of the set or not. So all of these macros or functions are provided to us by the operating system to create a set of signals. And then you can use this particular variable, right? This particular variable in the in the SIG action structure, right? In the SIG action structure here. So when you provide that set over here, it tells the operating system that while this handler is getting executed, you block all of these signals, not just one, but all of them, right? All of the signals which are part of Not sure how many slide I missed. Which slide I was at? Are you guys able to hear me? Are you guys able to hear me? Are you able to hear me?